There's one side.
Thank you.
Good. Anton, don't leave your laptop in here because we can't guarantee completely security. We can't go in here.
Okay.
So if you go for today, take it along.
Yes.
Other than that, what's all about with the work limit?
Yeah, I think for today. So tomorrow I'm going to get. When do you expect me to start here?
Yeah, usually I start with Sarah today. With Sarah, we started at 8. Is that all right?
I just want to figure out who's tomorrow stuff to do. Like, got my key number and other things.
So you think you can do it? You can do it tomorrow at 8 o'clock. We can of course start at Sarah and me. No, Sarah not tomorrow.
No, I can.
Because tomorrow, of course, we have the main conference, so there are more talks to upload. They're all quite short, and there are many more to upload. And so I will make an announcement in the moment that people have been putting their talks in the stick. And then, in the morning at 8 o'clock, I will upload it. Maybe I could even start tonight. But we'll always be pretty busy, sort of from 8 to 8:30 in the morning. Okay, good. Excellent.
Because that's when you come to their place at night.
What I do, you see, is I basically just put a new folder on the desktop that is whatever you can call it, day one.
Day one.
And then, or day one morning, day one afternoon. And then with they put their thumb drives in here and you copy it onto that folder and you give it a number based on the program. What is the first number, 1 to 10, whatever the order of the talk, so that when the session chair can open them, that they know this is number 1, 2, 3, 4, 5. With my glasses, wait, let me show you. Yeah, you see, I just did this basically. So not a lot today, from 1 to 9 with the name, so that whoever is the session chair knows, this is the next talk, to just click it and open it. That's all I do, how I arrange them in the morning. It's very simple, but it is a bit time consuming because for the main day, for the main conference, instead of 9 talks, we will have every day about 20, or 25 or something like that. So that's the only thing you have to do.
Okay, that's fine.
All right. Good. All right, other than that, accommodation, have you found something for the now until my wife is meeting?
For now, yes, and I'm going to Ram.
Okay,
I'm returning back on 15.
Yeah.
So I think we have to arrange it because, as I said, she already will leave by this moment.
Yeah, she will leave on the 40, when should we leave, on 15th or the 16th? Is she on the 16th? Maybe on the 16th, but we make a plan.
We will make a plan, and also before I leave to Ram, I need a place to store my bags.
So we can do it also.
Yeah. So, and then I think I'll find something.
And then for Finland, so I booked with the GTK people. They are here to we booked time at the Gluco Lab, for example, but that's only beginning of October. Now I asked GTK whether they can give us spin sections. I think it's okay, but they will probably send us spin sections from their intensity, which I made a portfolio of this. So they can start looking at the picture from the database, that you can start looking at.
So I believe in I will get back to Ram. Then I can start.
Computer or whatever.
I think I need to add. It'd be like, go to my Chrome, how I understand. Anyway, yeah, cool.
确认4点钟开会是。我这个就是今天休息的时候，今天和好多人就拉。
你不是他们人在吗？还是你也是要线上？
线上，线上，这是全世界各地的人。220，人都不错。半个小时，最后就写到，应该12:40到4:10才对。
查期的时候是，
他这就是半个，每个不是半个，他补到最后一个时间，完了3:40到4:20，都45分钟。我知道，就是那个，我知道，可是每个人都很短呢。哦，不一样，这个也是这也是，因为这个就是半个小时。我这个讲了，这个也讲了，不对，这是半个小时。半个小时。对，
但是你把电脑也带。
对呀，电脑带。
对。
然后我就听完他的。
对。
那个就准备他们。
也听了你。我忘给你找了个位置。
对，他给我找到他办公室去。对，这样子就安静一点。
对。
包括那个继续之前那个。继续我乱。像我们就是。
没推进来。
我当时一个人走。
中间文件。就回音，声音还能大一点。 maybe we just yeah, just a dream. Yeah, before that's good. Yeah, exactly.
So you don't believe in this band anymore?
No, from that time, not area, yeah. Size.
Okay. So I think the silver is doing this, but that's a map where they show that they have a map where they pretty much the same order and only quite sorry.
Yeah.
Hello. Signal work. I don't know why this thing doesn't work. Oh, gee. No, I can see it. Yeah. This, but I don't know how it works.
You start singing.
Hello, hello, hello.
Maybe it needs batteries.
I think I can see here some text, so I think it should be, there should still be battery in it. Yeah, battery is full. It's not the problem. I don't know what the hell is going on. Yeah, I know. When we ask questions, we have to speak a bit louder. To bring the background really hear us. The people ask the question also speak a bit louder.
So the other way, she's get speak to the question.
Yes, I don't know why the thing is not working. You as a young person perhaps understand it.
On-off switch.
Yeah, it does. Doesn't look like it. You see, this works. This thing doesn't. Maybe it only was because I just grabbed it from the other lecture hall. So that I can maybe do it, you know, I run around and if you want to turn it back on again.
No, it's fine, just.
Actually, no, I think you turn it back on again.
Once we're actually recording, it's fine.
Yeah, I know, that's right. It's still there. So I think as soon as you hit that, it'll come back again.
Okay. Oh, is it not recording anymore?
I just, so the little panel that came down from the top, I just turned that off. But having done it, I'm not sure if I know how to turn it back on again. Should maybe try when you ask, please speak up. People in the back can't hear you. The virtual delegates can't hear you. And if you can't speak up or don't want to speak up, then I will come closer to you and you can speak into this thing here. So this makes it much louder, but it's tricky. So we can try that then, but it is of course it's really fast.
Not down.
Just start this one. Oh no, it's under views. Go back to full screen.
Is that okay or no?
No, you want to be on full view. Presenter view. Oh no, no presenter view. No. There should be a full screen. Let's see how long it tells us. Oh no, it must be slide view.
Quite right either.
But that's not showing the full screen now. Oh, there we go. There we go. Yeah, that's it. So just minimize that. Yeah. She's up there with keys. No. Oh, hang on.
I'll just do that.
You know what happened there?
Sorry. The problem. We're stuck on how to move it back and forward.
Oh, the other thing I did, I just turned, I just disabled this thing. I didn't keep dropping down, but now I seem to have broken the presentation mode. So you can just go the hide floating meeting controls, and that just gets rid of that. So that shouldn't.
Okay. So now can we move back and forward?
But now we seem to have disabled the keyboard now. I don't know how to fix that. What's this? Let's just try end show and start again.
I think it's because you're recording in PowerPoint.
Ah, that's what's happening. We're recording. Yeah, we don't need to. We shouldn't be doing that.
We want to be we're recording the meeting, but we don't want to be recording in
The
PowerPoint.
meeting is still recording.
Yeah. I'm not sure how to fix that.
Those PowerPoint and stuff.
That might be the go. Yeah. Yeah, that's probably the best way to do it. Yeah, close PowerPoint, start again.
Hey everyone, welcome back. Hope everyone had a good lunch. We're going to kick off the afternoon session with a talk from Steve Barnes on MicroCT desktop and synchrotron XRF mapping of chromitites.
Okay, thanks, Brian. Hi, everyone. Yeah, so this is just going to be a review of some of the work that we've done in relation to chromite and PGEs over the last few years using combination of Microbeam Xray techniques. So I'm mostly going to be talking about 3D imaging using MicroXCT, and we'll talk a little bit more built from what I was talking about yesterday in the Wager and Brown. Of course, a lot of you weren't there, so some of this will, those of you who were here yesterday, some of this will be a repeat, but not too much of it. Okay, so just rough outline. I'm going to start a bit about talking some of the work we did a few years ago with Hazel Prichard on chromite in ophiolites, and then some of the ongoing work we're doing chromite in chromitites and the Marinsky reef, and talk a little bit more about these chain textures and some of the other 3D microtextures that we see associated with chromites, and then finish off by talking about some of the 3D imaging and 2D XRF imaging on sulfide PGM association in chromitite. So none of this is new, all of this is published, but the idea today is just to kind of bring people up to speed with what's been done over the last few years. So starting out with, let's see if I can get rid of this thing again. Chromite in ophiolites. So a number of years ago, I started doing some work with Hazel Prichard on some of the material that she'd collected and some of the material that was in the Cardiff University collection, mostly from Troodos, but also from some other ophiolite complexes around the world. And the premise behind all of this is something that Hazel had noted many years ago. If you look at the textures of chromite in ophiolites versus the textures of chromite in layered intrusions, they tend to be different. And ophiolitic chromites tend to be coarser grained. They tend to be more rounded. And they also have a number of sort of surface features, which we'll get into in a second. So typical layered intrusion grains are typically euhedral or slightly rounded. They're generally finer, and they characteristically form these sorts of chain and clustered textures, which we'll talk about later. So this is the kind of thing that Hazel had noticed. If you look at the margins of chromite grains in ophiolites, you notice that you often get these kinds of step features. And nobody had really paid a lot of attention to these things, so I guess they assumed that either there were fractures or there was there were just sort of some sort of alteration feature or whatever. But anyway, it turns out these grains that have these kinds of step features also very commonly have lots and lots of inclusions in them. So Hazel persuaded me to work with her looking at some of these things in 3D. And this is an example. This is from famous locality, the Harold's Grave locality in Shetland. This is part of on the Unst ophiolite. This is a very famous place, and these are some of the chromites that have the highest IPGE concentrations of any that are known about anyway. But anyway, this is a MicroCT image of a single chromite grain, and this is what these step features on the surface are. It turns out that they really are step features in 3D. And they have these very sort of characteristic kind of surface features. And also these grains have lots and lots of inclusions in them. And the inclusions turn out to be negative crystals. They all have nice sort of internal sort of crystal faces on them. So that's kind of intriguing. See that a little bit better there. So what we concluded was going on was that these things represented some sort of a transitional stage between an original skeletal style of growth, transitioning towards a more equilibrium kind of texture. And this is the sort of the cartoon that Hazel drew to suggest how this might happen. That you start out with these irregular, what are called sort of hopper morphologies, which are these sort of partially hollow sort of trellis kind of things. And then as these things grow, they gradually fill in the gaps and turn more and more into sort of regular conventional grains. But they leave behind these inclusions, which are basically inherited from the original dendritic structure. And this is an example of that happening in a different phase entirely. So quartz phenocryst from a felsic eruption, and quartz apparently does the same thing. It grows initially as dendrites and then gradually fills in to form these sort of strange kinds of textures. So that was the sort of the first encounter with these kinds of things. So then we looked at some of these. So these are nodular chromites from Troodos. These are some very famous samples collected back in originally the 1950s, I think. In these, you can see we've got these beautiful dendritic chromites. And we also get these nodular features. These are really characteristic, unique to ophiolitic chromites. You never see them in layered intrusions. But a lot of these nodules, the cores of them actually turn out to be dendrites. So we had a look at a few of these things in 3D. And here's some images of them. And a couple of things. One of them is that the margins of them are typically really beautifully sort of rounded eggs. So they've got really nice sort of smooth rounded margins. And sometimes the morphology of the nodule actually seems to have a sort of spinel-like morphology itself. And the reason that's happening is because it's actually controlled by the geometry of a single dendrite sitting inside the grain. So here's a couple of 3D images of this, and this one is an EBSD map of one of these kinds of things. Zoja is going to talk a lot more about this later on, although not specifically on this one. But what this is showing you, the color indicates the orientation of the crystal lattice. So here you can see that this is basically a single crystal dendrite. All of this is in the same crystallographic orientation, but surrounding it, you've got this aggregate, multi-grain aggregate, which are not in the same orientation. The orientation varies quite a little bit. It turns out this is an interesting sort of feature of this, that a lot of these grains actually share a single crystallographic axis with the dendrite core. They're not the same orientation overall, but they share one axis, kind of like beads on a string. Anyway, the important thing from the point of view of what I want to show you here is if you look at these textures here, they're really nicely annealed adcumulate textures. Now, these things can only have grown by some form of accretion on this dendrite core. So there's no way you could be making this texture here by compaction and sintering and melt expulsion, for example. These things have got to be growing that way, and they're growing by accretion on a pre-existing seed crystal of chromite. So that's kind of the takeaway I'd like to leave you with there. And again, so this is the cartoon that Hazel came up with and we published. Similar story, but in this case, we're actually accreting this population of grains around the rim of the dendrite. These things continue to grow to form these, presumably while these things are rolling around in the magma and in contact with chromite saturated magma, develop these nice adcumulate textures, this little rim. But then this thing's then finding itself in a situation where the magma's chromite undersaturated and they start to dissolve again. And that's what gives us these nice smooth rims. So these things are actually kind of rolling around in the magma and recording a progression of supersaturated, saturated, undersaturated with time. And that's what gives us these morphologies. And this thing up the top here, this is from Hazel again. This is an SEM image of a thing called a Graupel snow crystal. And these things are actually ice dendrites, which then get a rime of finer grained little ice crystals growing on top of them. And this is what we thought might be a nice sort of analog to what we were seeing in the nodules. Okay, so that's it for ophiolitic chromites. So now let's go back to our old favorite Marinsky reef. And those of you who were here yesterday have seen this image before. This is a Microbeam XRF map. For those who haven't seen a lot of these before, these maps are formed by the data is collected by rastering a sample underneath a collimated X-ray beam. This is done on the CSRO Maya mapper, which has the beam size is about 25 microns. So you generate a map with a pixel size of about 25 microns. And these images are made by stacking red, green, and blue channels with different elements in each channel. And typically for these rocks, we use chromium in red, iron in green, and calcium in blue. And that gives you, the orthoproxene comes out this nice green color. The chromite comes out orange, plagioclase comes out dark blue, and the clinopyroxene comes out light blue. This bright lemony stuff here is sulfide. So that's, we'll come back to that and show you some more of that in a bit. This is a sample of this material here, which is the basal chromite of the Morensky Reef. Johan talked about that just before lunch. This is, if you like, this is Brian's reaction chromite. This is the thing which is formed right along that basal contact. A feature of these is that they have these very distinctive, unusual amoeboidal shaped chromites in them. And so some of these things clearly look like they're dendrites. Others are just much more sort of irregular and blobby. Zoya is going to talk more about this, show some EBSD data on these things later. So I'll just move on and show you. This is a MicroCT image. This is all data that was collected by Belinda Godel at CSIRO when she first came and joined us as a postdoc. Here you can see the gray are the chromite grains. There's this sort of little cutaway here. The yellow here are sulfides, and the red are platinum group minerals. So you can distinguish these things really nicely. One of the things that came out of this study, which I think is really intriguing, is that the location of these platinum group minerals is not random. Where you find them, and that's shown in this histogram here. This histogram shows the frequency of the different textural associations of the platinum group minerals in relation to the other phases in the rock. And long story short, most of those platinum group minerals occur where you get a triple point between silicate melt, sulfide melt, and a chromite. And clearly that's some sort of nucleation phenomenon. The platinum group minerals like to nucleate on those high surface energy points, and typically where the curvature of the sulfide liquid is highest. But the other interesting point about this is that what it shows you is that these platinum group minerals, and some of these are quite big, some of them are quite coarse-grained, these things are nucleating after the sulfide is accumulated in the chromite. So these things haven't been collected by a sulfide liquid floating around the magma and then sinking. The platinum minerals are actually nucleating in the rock where you now find them. Now, having said that, I should say this is one study in one place, and this really needs doing more extensively elsewhere. If this holds up, then I think that's an interesting conclusion. Okay, so let's have a look a little bit more on the morphology of these kinds of chromites here. And this is an animation of a CT scan through one of these samples. This is a slightly different sample. But again, you can see here, these are these beautiful, strange amoeboidal chromites. And one of the things you notice here when you look at this is that a lot of these things that appear to actually be inclusions in the chromite are actually not inclusions at all. They're actually complicated 3D embayments. And that's something which is not at all apparent in a 2D thin section. So, and I think that's important from the point of view of interpretation. These so-called inclusions in chromites, a lot of them are probably not really inclusions at all. Here's an example of one, and this one sort of harks back to what I showed you, the ophiolitic chromites. This is a big single chromite here, and these things are negative crystal inclusions, which are quite commonly found inside these really irregular grains. And what we find, if we go back to the beginning again and look here, what you see is that there's actually kind of a bimodal distribution. You get the amoeboidal chromites, which tend to sit right along this lower contact. But then within this chromite string, remember this is only a couple of centimeters thick, within the stringer itself, you get these much more regular fine grained, sort of sugary kind of chromite grains. And these are the ones that show the chain textures. So we'll move on. So this is and this is from the paper. This is Zoya's paper from her PhD, I'm sure she's going to say some more about this later. So I'll pass on to the next bit and look at some of these sort of sugary chromites that we find within some of the chromite seams. In fact, we find this kind of texture in pretty much all of the chromite seams, but it's easier to see in some than others. This is the UG1 chromitite. Famous Drouaz River locality. You've already heard a bit about this today. A couple of interesting things. That's the top contact of the UG1 chromitite. These things here are plagioclase. Just get the laser pointer going here, sorry. These things here are plagioclase oikocrysts. And you can see they're quite euhedral, quite idiomorphic, and a lot of them are actually growing down from the top contact. So these things are clearly growing within a mush. But the mush texture is really interesting because it's got a very open framework. So this is just a regular thin section. You can see here these chromites tend to form these little sort of, I call them caterpillars when we first started to see them. These are very distinctive sort of in 2D chains, in 3D cages and frameworks. And here's some details of them in 3D. Rais showed some really nice images of these yesterday. But so that's this is typical UG1. This is a typical stratiform chromite sitting on a originally planar, presumably more or less horizontal surface. Here's another one which Rais has showed you some pictures of. This is turned up a few times today, and this is where we get chromites along the vertical dipping sidewalls of potholes. So we'll just take a look at it. This is an XRF map of one of these things. And you see a lot of the same features that we see in conventional standard sort of stratiform chromite. We see truncation of layering in the anorthosite footwall. We see this very fine, pure anorthosite, very clean, pure anorthosite rind. But what I want to focus on more here is that we also see these beautiful caterpillars and chain textures within this sidewall chromite. So we can be, I think, 99% at least confident that this chromite grew where you found it. This grew on the sidewall. It clearly didn't grow by some sort of gravity settling kind of process, or any sort of gravitational deposition. So what we decided to do then is to try and find a way of actually kind of quantifying these kinds of textures and trying to make the interpretation of these things a little bit more objective. And I think one of the problems that we often have with looking at these kinds of rocks is that the human eye is really very strongly oriented towards seeing patterns. The human brain just wants to see patterns in everything. And we particularly want to see patterns that reinforce our preconceptions about how things form. So, and that's one of the big problems, I think, with this whole sort of area of science, because so much of what we do is just based on observation and qualitative interpretation. So trying to think, are there some ways we can actually maybe sort of make that a little bit more objective? So one thing you can do is you can look at packing densities, which is just the proportion of the rock which is actually made up of the liquidus phase. We can look at grain size distributions, and that's what we've got here. This is a crystal size distribution plot of chromites from the UG1. These are determined from the 3D image, so you don't have to correct them. And what you see is there's quite a range in grain size. There's a big peak around at sort of 80 microns or so, and then it kind of tails off, and you get very small numbers of grains up to sort of 500 microns or so. But I should point out what we've done here is to select an area, select a volume which is enclosed within orthoperoxine oikocryst. So we think these things are recording the original grain size before you had any post-cumulus sintering or recrystallization. And then what we've done then is to compare that with computational simulation, which is basically taking a population of grains with that exact grain size distribution and generating a simulation which basically makes a gravitational pack. So basically just dropping them in a bucket and looking at the characteristics of the grain pack that you generate. And there's various different ways you can do that, but this is the one that we came up with. And there's a number of parameters that come out. One of them is the packing density. For this particular grain size distribution, the predicted packing density that you get from these is about 60%. In other words, you'd expect a rock which is 60% crystals. Now, if we compare that with what we actually see, that UG1 sample that I showed you is actually 27% crystals. That Morensky Reef sidewall sample is 53% crystals. So they're both considerably less than the theoretical packing density for just basically dropping loose crystals on in a bucket. Now, the other thing we looked at, and this is sort of the more sort of innovative thing we did in this study, is to look at a thing called the coordination number. And the coordination number is the number of crystals, the number of chromite crystals that each chromite crystal touches. And this is basically a way of measuring the openness of a framework. How many grains does each grain touch? So this is the blue simulation here. That's this model. And what that shows is that you expect a more or less linear increase of the coordination number with grain size. And that's kind of intuitive. So the bigger the grain, the more other grains you would expect it to touch, right? If we look at the UG1 sample and we look at the Morensky Reef sidewall sample, we find that they both fall well below this distribution. So down at the bottom here, typical sort of coordination number of around about sort of 4 or 5 for the average size grain. But if you look at the bigger ones, then you notice that the observed distribution starts to diverge considerably from the theoretical one. It's a bit different. The Marinsky reef chromite is still linear. The UG1 chromite distribution tends to flatten out. But the point is they're both distinctly different from the theoretical loose pack one, and they're quite similar to one another. So again, this is just one study, but I think this has got some real potential as a way of putting some different kinds of textural parameters on cumulate rocks. So I say the model predicts a linear increase with size in the grains. The observation is that the curve flattens out above a coordination number of about 8, and that the UG1 and Marinsky reef sidewall are similar. Why is that? It's because of this chaining effect. It's because the grains are not just randomly distributed. They're not just shaking around in a box. They're connected up to one another, and that effect reduces the coordination number. But the texture that we see in UG1 is similar to that for demonstrably in situ grown sidewall chromite. That's really the takeaway here. So what are these things? Well, we had a lot of discussion about what these things mean yesterday. I won't sort of rehearse all of that argument. What we originally thought was going on with these things is that we were seeing some sort of heterogeneous nucleation, which is when crystals grow against a pre-existing solid substrate. And we thought what we were seeing is evidence that chromite crystals were nucleating off pre-existing chromite crystals to form chains. And there's all sorts of reasons why that simple model isn't right. I won't go into all of that, but I just want to show you some experiments that we've been just one of a few experiments that we've done recently with Zoja here. This is an experiment taking a Hawaiian basalt, doping it with a bit of extra chromite and olivine, cooking it up cooking up in air to about 1600 degrees. So all of the olivine and almost all of the chromite dissolves, and then re-equilibrating it again at a lower temperature. So what we're doing here is we're growing chromite from a very significantly chromite supersaturated liquid. And what do we get? We get these little chains. And I'll just show you one of these in 3D. I've persuaded this to run. There we go. So this is a MicroCT scan of this experiment. What you can see here is that the chromite's very heterogeneously distributed in the sample. And where we're getting clusters of these little new grains growing tends to be around where we've got the remains of the chromite that didn't melt during the preheating step. And those are these big ones here. These are kind of leftover unmelted chromites. But these things seem to catalyze nucleation. There are a cloud of crystals around them. And most of those crystals, they don't nucleate directly off that grain. They're nucleating independently. It's homogeneous nucleation, but the homogeneous nucleation in clouds around pre-existing seed crystals. And we think that's the phenomenon of secondary nucleation, which I spoke about yesterday. So I just wanted to show you this one. This is nothing to do with chromite, but it's such a cool image. I wanted to show it to you anyway. This is an example of growth of a phenocryst cluster. So this is the classic glomeroporphyritic texture. This is an andesite from Tongariro volcano in New Zealand. This is a sample from Teresa Ubeda at the University of Queensland. This is another microXRF map. This is a synchrotron XRF map. And we're showing chromium in red, titanium in green, calcium in blue. And what that does is it gives you it shows up orthoperoxine and clinoperoxine. Clinoperoxine shows up in these pinky colors. Orthoperoxine shows up in these reddish colors. And we see we're getting an intergrown cluster of 2 peroxines. And this banding here is fluctuation in the chrome content. So this is classic oscillatory zoning. But look at how the same zone seems to be traceable through the orthoperoxine and the clinoperoxine. And also you can see that the grain size is really tiny in the center of this cluster and then gets bigger as we go towards the outside. So this thing is starting out as a little cluster of crystals and then growing out to form these beautiful sort of snowflake aggregates. So make of that what you will, but I think it's a really interesting phenomenon. So that's just the same thing in a bit bigger, glorious Technicolor. So that one's going to be on my wall fairly soon. Okay, so well, what's the significance of all this? Well, I don't want to get too much into sort of genetic models and all the rest of it, but I did just want to make one point, and that's in relation to Wolf's talk and Wolf's model for formation of these particularly chromite, peroxenite, and orthosite associations by unmixing of gravity flows. And this is a really nice experiment by Farian et al. I think this was done in Sarah's lab, I believe, yeah. And what she showed is that you could mix up sort of populations of beads of different sizes representing different phases, plagioclase, peroxy, and chromite, run these things down a slope, classic gravity flow, and what would happen is that the finer material, which is in this case is supposed to represent the chromite, segregates down to the bottom of the flow. And this is a thing called sometimes called the Brazil nut effect, and it's the same effect if you take a jar of nuts, mix nuts, Brazil nuts, and peanuts and hazelnuts, and you shake it. What happens is the Brazil nuts rise to the top. And the reason is because the smaller grains migrate down through the interstices between the larger ones. Okay, so so this is the explanation which has been offered for forming chromite seams. But the point I want to make is that for this to work, all of these grains need to be non-interacting individual particles. Anyway, this assumes that your chromites are little independent grains that are behaving just like little rice grains. But we've seen that they don't do that. We've seen that chromite grains in these kinds of rocks actually form these quite big chains and clusters. And if you look at the size of them, these things, they're several centimeters across. So if we accept the conclusion that I've been arguing for before, that these things are growing in place, then that kind of rules out the idea that you can make these things by just sort of unmixing a loose crystal pack, because that assumption that the grains are non-interacting individual particles doesn't hold up. Okay, so I don't need to explain this. We can skip over this one a little bit. So let's go now. How am I going for time, by the way? 5 minutes? Okay, yeah, that's fine. So just the last bit of this talk, what I want to show you now is some more Morensky reef work. There's a couple of samples of Morensky reef. You've seen this one already. There's the so-called pegmatoid on top of an orthosite, chromite seams on either side of it, a peroxenite above. And that's images enhanced to show where the sulfides are. And that's image is enhanced to show where the platinum grains are. What you see is that there's a sort of a peak of platinum grains, particularly associated with the chromite seams, a little bit extending up into the peroxenite. But every single one of these platinum, called platinum hits, because they might be sort of composite grains, every single one of them is associated with sulfide without any exceptions. But the other interesting thing is that if we look at the proportion, so we just do sort of a number count of the number of platinum hits versus the sulfide mode derived from this image, what you find is that the proportion of platinum to sulfide is much higher in the chromite seams than it is either in this orthosite below it or in the peroxenite, higher by sort of a factor of maybe 4 or 5. So this kind of fits with the idea. It's an old idea which was proposed by Tony Noldrick many years ago now, that sulfides in the chromite seam actually preferentially kind of remelt or disappear as a result of interaction with the chromite. And it's a complex mechanism that involves defect structures in the chromite, which I won't try and explain. But that seems to fit very nicely with what we're seeing here. So if we assume that was originally a homogeneous sulfide phase, the sulfide in the chromite seams has systematically redissolved or somehow or other disappeared and left the platinum behind, which accounts for that change in ratios. One other point about this one, which is kind of interesting, there are a few big grains here. In this area, there's one big platinum grain here. It's a platinum iron alloy grain. It turns out that over this entire sample, about 40% of all of the platinum in the sample is in that one grain. That's kind of a scary thought. If you're sampling these things and trying to get estimate platinum grades, then you've got a bit of a sampling nightmare. And I think that extends through that problem extends through a lot of platinum element geochemistry. That platinum in particular shows very profound nugget effects, which we're not always aware of. Okay, so what else did I want to show you here? We'll leave this. Well, this is just to show you again that we get the same relationship in the sidewall Morensky reef. There again, it's the sulfide and PGMs, and again precisely that same relationship. I think I'm probably running out of time to be able to talk about this, so I might just cut to the chase a little bit, or at least just kind of gloss over it. So this is again going back to some work I did with Hazel. This is Hazel's unique sampling technique for getting platinum group mineral grains out of chromite seams. This is what we call the Hazel Prichard Memorial Aquatic Complex, which is an inflatable paddling pool on the side of a mountain on Unst. This is the Harold's Grave chromite. And what Hazel was doing was panning the drainage out off this little outcrop to pull out platinum group grains, because this is you remember the Harold's Grave locality is the one where we get these astronomically high sort of 10 ppm concentrations of iridium group metals, way higher than we see anywhere else. So we did some microtomography on these things, and on these chromites, I should say. And what we found is there's basically two significant populations of platinum group elements. We get inclusions, enclosed laurite and osmium iridium platinum alloys. These things occur within the chromite grains that's universal. We always find that in chromite, no surprise there. But what's different about these ones is we also get these coarse-grained polymineralic aggregates of, again, IPGEs developed interstitial to the chromites. These things are always sitting outside the chromite grains, and the single laurite type, osmiridium alloy, those types of assemblages, those are always inside. So this is a sort of fairly well-established model for formation of the iridium inclusions in chromites, and that is from the classic paper from Finnegan et al. 2008, where they showed that if you've got a chromite crystal growing, it generates a redox boundary layer. Within that redox boundary layer, you can nucleate iridium grains, and they get trapped in the chromites. Basically, PGM are nucleating an Fe3 plus reduced boundary layer, and the reason for that is because of the really strong FO2 dependence of PGE solubilities. Now, here's another study which bears on this. This is a really interesting one. This is by Fonseca et al. And they were trying to explain the origin and long-term stability of osmium iridium alloys in the Earth's mantle. And long story short, what they suggested was going on was that you formed osmiridium alloys in the mantle as a result of dissolution of sulfide. So it's sulfide mass reduction by dissolution into silicate melt during partial melting. What that does is it increases the IPGE concentration in the sulfide. And when it gets up to a few hundred ppm, that's enough to stabilize these phases. And then if the sulfide then completely melts and disappears, then you leave behind these phases in the mantle. And these are the things which are the basis of rhenium osmium model ages in mantle rocks. So that's what we thought might be going on here. These two different PGE populations, one is formed by the usual way, inclusions of iridium alloys. The other one's initially starting out as a sulfide, and this sulfide is then partially remelting, partially or completely remelting. And as that happens, it forms these coarse-grained aggregates of osmium and iridium. There is some sulfur in these things as well. We get these strange ruthenium pentlandites and so on. If you time it just right, you can also make platinum alloys in these things before the sulfide disappears completely. And indeed, we do get anomalous platinum in some of these samples as well. So what we think we're seeing here is the result of a initial growth of sulfide, probably also within a boundary layer around growing chromite grains, possibly due to local iron depletion or redox changes or whatever it is, something or other causing sulfide to nucleate immediately within the vicinity of the growing chromite grains. Now, here's an interesting point. So if we're growing chromite from a magma, we know that chromite requires of the order of 100 to 1,000 times its own volume of magma to grow. That's just the concentration factor between a silicate melt and chromite. So if now that chromite has got 1% sulfide in it, that 1% sulfide is now seeing 10,000 to 100,000 times its own volume of magma. In other words, it's seeing a really high R factor. That's what we need to get really high PGE concentrations into the sulfide. So we've got a few factors all working in the same direction. We're probably nucleating PGMs in this boundary layer. We're nucleating and growing sulfide at very high R factors, getting very high PGE contents. And we're then flushing this with sulfide undersaturated magma, redissolving that sulfide and leaving behind our PGMs. And that mechanism works not only for our Harold's Grave situation, but potentially also works for conventional chromite seams in layered intrusions. And the reason we get such variable proportions of the different PGEs depends on how far that process happens, how much sulfide we leave behind. So, and that's all described in this paper that we published in Canadian Mineralogist last year. Those are my conclusions, and Brian wants me to stop talking. Thank you.
We have time for one quick question.
For your last presentation, is the sulfide getting dissolved? How is about fluids in this system?
Well, it's possible that there might be fluid related, but I don't think it needs to be. I think the chromites are forming from an which is essentially chromite, sulfide undersaturated. But you get transient sulfide saturation just in the boundary layers around the brine chromite. And that's why when you look at these things, you see sulfides only associated with those chromite seams, and the rocks are immediately adjacent to them. As soon as you go above, sulfides disappear. So it must be a transient saturation for me. So I don't think you need some sort of additional fluid component, but you can't.